3D optical manipulation of photopolymers, and this is from McLeod from the University of Colorado.
Thank you. All right, so let me, since it's been an entire day, let me remind you what I said last time. If you take a solid polymer host that's rubbery, and in this case, I don't really care that it's rubbery, but that means diffusion can happen. And you put into that rubbery solid three things: a dye, or a photoinitiator, some sort of inhibitor, which likes to eat that dye when it gets excited, and a monomer. Then what can happen is a photon can come in, it splits that dye into radicals. Those radicals may be eaten up by the inhibitor until that inhibitor itself is removed from the system. And then when that inhibitor is gone, you keep making radicals. Those radicals attack the monomer starts joining up and making polymer. And so far, that's just polymerization, photopolymerization, nothing magic there. But because we're living in a three-dimensional solid host where diffusion is possible, you've now made a hole in the monomer concentration. Monomer will diffuse in to replace what you've eaten up, because monomers are small, and that mass transport gets you a local index refraction change. The addition of that second chemical in the way, the inhibitor, as I showed last time, allows you to go in and get features that are constrained in their size, so you can use only one photon chemistry and get some diffraction features and not have the whole material depolymerizing, etc. So I got a beautiful question from the woman who was giving me all the great leading questions. I don't see her right now. Who said at the end, how do you get control over that pattern of inhibitor? So what I showed last time is you get some control over that pattern by carving a hole in it with the same beam that you're writing. So that writing beam comes in, it makes these excited radicals. Those radicals eat up the inhibitor locally, and then that makes sort of a near field mask in 3 dimensions, which you can use then to control the polymerization. But that's a little bit like trying to do 1 or 2 or 3 things with just one knob, and so clearly it's a little bit limited on how far you can go with it. So my 4th lecture, one after lunch, this is to convince you to come back after lunch, will show you how to get independent control of that inhibition pattern and get well below the fractional order of magnitude or so. But as I said, and I apologize to all the physicists in the crowd, so I think that's most of you, is that I am an engineer and so interested in applications. So I was going to do this lecture on the applications of what I talked about in the last 2 times. And it turns out there's a whole bunch of those, which is why I think the materials are fun. Most of this is my work, just because that's something I can talk about easier. If I'm not communicating to you and you don't understand anything I'm saying, it was a complete loss. I don't care if I don't get all through this, is what I'm saying. So stop and ask questions. Some of these things have developed from the basic idea to something relatively complicated now in application. So if you want to stop and talk about and just dig down into one application, that's fine too. So, first I'm going to remind you of holography, because my machine decides to pay attention to me here. Hello. I listed lots and lots of applications. I'm not going to talk about all these. Particularly down here, I won't talk about too many of these things. Holographic optical elements, lenses I mentioned before. You can make really great filters out of these materials. Those are used in astronomy. And we've already heard a little bit mentioned in the talk this morning about polymer dispersed and polymer stabilized liquid crystals. So I won't talk about those too much. There's things that I will talk about. Mainly I'm going to talk about volume holography, because the materials are really good at that. A lot of my work is on integrated optics. And I guess I already talked about that already. So basically, we'll talk about holography and doing waveguides and interesting things like that. So let me give you a little reminder. I guess, can we turn the lights down? Nice little black background. Let me give you a little reminder on volume holography, in case you don't remember that. If I take 2 coherent beams, let's say a plane wave, I'll call the reference, and let's just do some interestingly shaped beam, like a spot that's diffracting out. Those will create an interference pattern in space. If I shove one of these materials into that interference pattern, of course, now I've got a local variation of intensity. I can copy that variation of intensity, if we do all the things we talked about yesterday, into an index of refraction variation. And then if I bring that reference beam, sorry, yeah, you made a difference just the wrong way. So that's good. If I bring that reference beam in and interfere it or diffract it off of that volumetric pattern, I can recreate the object beam. If I say the word Bragg selectivity, does that ring a bell with most people in the crowd? Volume Bragg selectivity? Okay, I got at least a couple nods, and they weren't all 20, so I'm good. Because that's what we're going to use for a lot of these applications. One important little detail, which I'll exploit next, is if I take this reference beam and I phase conjugate it, that is, I run it backwards, instead of playing out the object, I play out the phase conjugate of the object, time reverse, and I'll recreate this beam, and that turns out to be a nifty little trick, which we'll use next. So the materials that I handed around last time were developed by a company that spun out of Bell Laboratories, now called Interface Technologies, and I collaborated with them there in Colorado. And their reason for existence is holographic optical data storage, and that's what developed those materials. So let's again, stop me if you're not following this, but it's fun stuff. So the idea is we're going to take a disc, a slab of this material, it'll be 1.5 millimeters thick. It's going to look like a CD, maybe a little bit thicker. We're going to bring in one of these reference beams, same as I had last time. But the object beams, instead of being a single diffracting point now, is I'll bring some light in. I'll go off of a liquid crystal spatial light modulator here. And I'll have 1.4 megapixels in that page. This is binary. And that's, with appropriate digital coding, is going to represent a megabit or so of information. I'll interfere this single reference beam and that megabit of information in the material. Then I'll rotate the reference beam by milliradian or so. I'll bring in another page of data, and I'll keep doing that. When I finally have exhausted all the delta n I can get of the material, I will step over, I will do it again. And the idea is to get to terabyte-ish storage on a single disk. Obviously, this is write once, because you do this once, you do the fixing procedure, and you're done. Good so far? It's a little more complicated in practice. This is what their drive looks like. They actually can sell you a drive if you'd like to buy one now. They're a 3.5-inch form factor. It looks kind of like a tape drive. 50 milliwatts of blue laser. You come up, and here's oh, sorry, you missed something important. We'll go back to the basics here. To read this out, so I recorded this with the reference beam here. If I was to then replay the reference beam, the light would continue on this way, the diffractive light, and I'd put a lens or something and re-image the data onto an SLM. The difficulty with that is the aberrations, etc., that build up in the system. This is a pretty high-quality imaging system. You want a very small spot here, so you're going to run about F1 optics, which is non-trivial. So what they do instead is they run the reference beam backwards to read out. That sends the light backwards out of the system, back to the same lens, and then back onto the camera. And the really nifty thing about that is it keeps all this important stuff on one set of disks, which keeps your mechanical engineers happy. But the tilted material, perhaps imperfection from the lenses, God knows what, all those aberrations are phase conjugated and corrected. And that's a pretty nifty system now. So that's the reason we get both the SLM and the camera locked in place up here. Really pretty clever idea. This is what that looks like. We've got some motorized half-wave plates here, so I can switch the light nodes between read and write, bring the light onto the SLM, bring it down into the disk. There's some cleverness here with some of the optics, which I could talk about for weeks, so I won't do that. Reference beam is split off. I got some galvo here, so I can adjust its angle. Notice this funny galvo hanging in the back of the disk here, which I've tuned off so that nothing happens. Because it doesn't get used right now, and I record my holograms. To read it back out, I rotate this little half-wave plate so I can send all of my reference light on every photon I can get to the reference beam now. And I put this little galvo here to be retroreflecting, so light goes through the disk, which does because some diffraction go this way, goes backwards, and then sends some diffraction back this way, and onto the camera. Pretty clever system, actually. That's what it actually looks like in reality. This front faceplate here is about that big. Whole lot of optics packed into one box. And again, we could spend all sorts of time walking our way through that. But the point is, from the simple idea of, oh, there's two beams in some material, when we actually turn it into a product, it's something more complicated. Sitting over here is a FRU, or a field replaceable unit. That's industrial talk. That's where the 405 nanometer diode laser goes. They worked with the company that makes these things, if you know who that is. Because the problem is the lasers don't have enough lifetime these days to go into a product. They are getting better, but lasers run out of, even 405 lasers run out of steam in terms of lifetime. So they had to, of course it's got to be nice and beautiful and coherent because I'm doing interference with it. The 405 diode in your DVD player or Blu-ray player is not going to have much more than a cavity length or 100 microns worth of coherence length. This needed a lot more, so they had to make their own external cavity system with a tunable rating. They also need to be able to tune the wavelength because the material shrinks and expands with temperature, and now that changes your drag condition, so you have to both change angle and change wavelength to bring those holograms back into the readout condition. Lots and lots of servo optics there to make that happen. And then all this will break, so instead of having to send the whole drive back to them, they can, it's mounted on rails, you can pull it out and pop a new one in. So this, this picture that says, I kind of like to show this because in this picture here it says laser. That's what it looks like. So this is the realities of turning simple physics into products. So there's a lot of them. I mentioned last time, one of the cool things about these materials is you can get high optical quality without ever doing polishing as you would do in a crystal. And this is just a kind of an example of sometimes the form factor, in this case this material that solidifies, giving you capabilities. They're kind of clever and cool. So this is their disc manufacturing process. And there's machines that do disc chunk and out comes a disc. Here's the, you see this looks like a 5-minute epoxy applicator, right? You've got 2 tubes up here, and it is, exactly, because the matrix material, the urethane that is the 95% passive optical material, has got a hardener. When you mix the two together, 5 minutes later it's going to become solid. So this machine goes squirt, mixes these things together, and lays out a ring of this on a disc. Plastic substrate, looks a lot like a CD substrate. It's cast, it's got servo marks and their important stuff in it. Then you squeeze them together, and out comes this sort of polymer sandwich, flat. Not shown here is what's holding these substrates are 2 vacuum chucks that are pulling the substrates against steel that's been polished to be optically flat. So even though these substrates are wobbly plastic things, about 1 millimeter thick, you pull the outer surfaces optically flat. Then when you squeeze this thing together and it cures up to a solid, the whole thing stays optically flat. These are darn clever. So they use the polymer sandwich in the middle, the mayonnaise in the sandwich. Once it solidifies up, it compensates for any remaining interior variations you've got, and the exterior, which you've held against these ground steel flats, stays flat. And this is an interferogram, a Heaney light, and they're just damn flat. So they're really easy to make high optical quality, and that's one of the cool things that the materials give you. I got a couple of furrowed brows on that. Does that make sense? You're still thinking. All right. Here's what the discs look like in terms of data once you actually start making that into reality. This is that disc that Tom's living in here. This is about the size of a CD. These are basically the tracks. Each one of the width of these things is the size of the reference beam and object beam on the disc. You start playing those out across here and laying lots of holograms. These are called pages. For some historical reason. This is that 1.4 megapixel page. All little black dots are places that they put various codes to do alignment and other clever things. And you can see there's all sorts of bits and twiddles in here to make the whole thing work. Because once you get with the page analogy, your engineers run wild with terminology, and so you start making books and stacks and libraries and various things. But we'll just go as far as books. You take a page and you multiplex in one location 320 pages. That's just by tilting the reference beam. So that gets 1.4 megapixel times 320 at every location. Then you move over and do that again and build up books. And eventually you lay down 16,000 of those books. When you go all through that, that makes about 1/3 of a terabyte on a single disk. That's their first generation product. And by the way, that is a big number. It's just a lot of data to manage. It was a little amount of work to make all this happen. There's been a book by Sinterbach out for years on holographic data storage. These guys, Kevin Curtis and all, just made a new book, and so it just came out like in the last month. So if you want to know more about it, this is sort of the state of the art on all those bits and details to make that happen. A lot of fun.
And Bob, it's all one color, is that right?
Yeah.
Okay.
Yeah, I mean, you can do wavelength multiplexing. There's about as many multiplexing methods as there are researchers that ever worked in the field, each with their own name. It's just not very practical in a drive. It's hard enough to get that one color when you use that laser unit. So you could theoretically multiplex a whole new set of data there at some other color, but then you could have that second laser nuance.
Do people use different polarizations as well?
The holograms themselves are not birefringent or anisotropic, so that they would play out in either polarization. I think the short answer is similar to what I just told Tony, is there are a lot of tricks you can pull to increase capacity. For example, the reference beam is a plane wave, and that's essentially shift invariant. Well, I could make that reference beam something complicated. I can run it through a phase mask or something. And now, when I move the disk just a little bit, it looks different. Well, you can use that as a multiplexing technique. But now, if I can't get the disk right back to where I need it to be, then I can't read it out at all. So you have to kind of go through all the different options and sort them against getting the performance you want, which is hard because it's a big number, and you can build it. And so you end up, this is essentially angular multiplexing was the first method ever proposed, and that's what's in the product because it's the simplest thing. All right. So this is a relatively complicated box. I guess it would be a really complicated box. And that motivated ideas of could you do really high capacity storage, but maybe not need that much optics in the box. This is work I did with Parnell at Stanford. This, except that it's done at green light, is essentially a CD. I got a laser, here we're modulating an AOM instead of modulating a laser, but same difference. And I bring it down to a disk, and then I take reflections off of that disk, and I detect something. So that's a cartoon of a standard drive. And what we said is, well, maybe could I figure out how to get to multi-layer in here? Because what makes these materials interesting for data storage is I get thickness, and that allows me potentially to get a lot more capacity than just storing on the surface. So could I literally use thickness? So in real space, as opposed to the Fourier space of the holographic data storage, the page base. Well, I can think about writing little index blobs here and then trying to reflect off them or something, but it turns out there's some fundamental theories relating to the coherent transfer function of this microscope that says you couldn't see those, and they're not efficient reflectors. So I need to do something to make those little blobs efficient reflectors, and I need some ability to separate them in depth. Well, separating them in depth means I need a confocal pinhole here that would allow me to see different depths. That's well known, that's easy. Making them something that would actually reflect turns out to be relatively easy too, because I add a retroreflector. I could use a cat's eye, I could bring a laser around and send it back up, whatever I want. But what I want to do is I want to intersect, right at the focus, these two Gaussian beams, so that I have them perfectly overlapping. A little bit of an interesting problem for a product there, but that's the problem of mechanical engineers, so we'll go with that. And make a tiny little standing wave pattern that's a retroreflecting hologram that's order micron in scale. So that is actually realistic for how many fringes there are. So it's a hologram, but it's got a count on the number of fringes. And then each one of these little bits is one of these little microholograms, and its presence or absence represents a 0 or a 1. And we did that. So we're going to take here's a little cube of polymer. We're going to move it by, on a standard CD motor, moving at standard CD speeds. Believe it or not, that's pretty darn fast, 20 meters per second. So I think we probably have the record here for holography in a moving material in terms of speed. And we'll make about 1 by 1 micron bits, separate them by about 10 microns. We worked in a relatively thin layer of polymer because of aberration reasons. One of your lenses would have been a great thing here so that we could have reached deeper in the material and corrected the spherical aberration. And in this case, we got up to around 9 gigabytes, and a few years ago that was exciting, not so much now. One of the neat things is the data codes, the storage codes used in data storage are not 1010. They're actually different length marks. This is called run length encoding. And there's a trick you play there. You get greater capacity than writing on-off marks. Well, the neat thing about this pattern is that the material is moving by. Notice these fringes are parallel to disk motion, so we actually do write holograms into the material while it's moving, and we just smear out these longer holograms, which is kind of weird. The thing that makes all that work is the times that are represented at times here are so fast that vibrations don't exist. So you don't need to do vibration isolation. There's just no acoustic frequencies that are moving stuff around in a nanosecond time scale, which is pretty neat. And so then you go down to the disk, it's moving at 20 meters per second, you write multiple layers, you write multiple tracks, you fill up this whole disk, then you expose it to incoherent light that fixes everything, and then you come back and there's all your data. A little bit noisy, that's a feature that takes a lot of work to get rid of these materials, as they do tend to be a little bit inhomogeneous on the submicron scale. But the data's there, and your coding engineers can recover that for you.
So what's the difference between the three?
Those are three different layers, I'm sorry.
Oh,
Third, fourth, and
layers.
fifth layers. Yeah. So those are right on top of each other somewhere in here, separated by about 10 microns. And the confocal pinhole is what's allowing you to distinguish them so that they can do that. This has actually got a fair amount of industrial interest. Sony's trying to develop a product on this. A bunch of European startups have started. Some German universities are working on it. So there's a fair amount of interest in doing this, simply because the drive is so much simpler than the complex page-based thing I showed earlier. That maybe this is a fourth generation product that you can, even if you cross your fingers behind your back when you're talking to people, think that this could potentially be backwards compatible with existing products, because it looks sort of like existing products. I don't particularly believe that, but if you're trying to get money, you could say that. I didn't do that. Good so far? This is the Jedi Master level now of manipulating photopolymers, so if you follow this, then the lectures have been a success. The problem with the previous thing, believe it or not, because I actually was in a company and we were trying to commercialize it, is this retroreflecting head over here caused the mechanical engineers hell. And the problem is, I make fun of this, but it's a problem, it has to be co-aligned to light coming down to sub-micron, in fact closer to 100 nanometers in all three dimensions. And yeah, on an optical bench, that's no big deal, but in a drive that's sitting on somebody's desk that you make for 30 bucks, turns out that's a big deal. So the mechanical engineering team kept saying to me, leading the optics team, can you make that go away? So what do? You get lots of caffeine and you say, how can we do holography with only needing one beam? Which is the wrong question. But the right question is, how can we do holographic data storage needing only one beam? And that turns out to have an answer. So what if we were to structure this material with a big reflection grating, basically one big bit, and it's got these little fringes everywhere in it, so that it's reflective everywhere. If we scanned our confocal microscope around everywhere in this bit, or sorry, this disk, we would see light coming out. Okay, so we've filled it up with ones, if you will. And then we asked the question, could we take this region where we got this grating and blow a hole in it? Somehow destroy it, muck up the reflectivity, change the phase, change the amplitude, something like that. So that now this, for example, would no longer efficiently reflect because it doesn't have this high frequency reflection grating, which is going to send light backwards. That now is something you can only do only with one beam. And like I said, this if you don't follow this completely, it's not a disaster, but it does give you some idea of the complexity you can build into these materials. This is just a diagram for the optics folks in the crowd to say, God, aren't we great optical engineers? Let me go back and circle there. The other thing that the rest of the drive team tells you from, let me go back one more slide, from this thing, is that looks really great, but notice there's no servo marks in there. There's no way to know where this focus is. And a big part of what makes your optical drive work, particularly the ones you jog along with on your hip, you know those things are maintaining about 30 nanometer accuracy tracking, and you can jog with them? The power of servo, which is the servo marks in there that tell the head of how to align itself. This lens is sitting on little voice coil actuators, and it's sitting there vibrating around and tracking the disk motion. Well, this doesn't give you any features to know where to be, and that turns out to be a big problem in getting it from an optics bench and into the product world. So we needed to find a way to put tracks in this disk, and they needed to go in depth. In the CD, you stamp the tracks in the original mold that makes the CD, but we want to be in depth, so stamping doesn't work too well. But we're optical engineers, so we have optical hammers. So what we're going to do is we're going to take this reflection grating that we want everywhere in the disk, and we're going to put a couple extra beams in there, get a moire pattern. So we get a grating here, but it cancels out, and then it comes back, and it cancels out. And we'll do a couple little 3 or 4 beam holography, and we'll create this pattern. So now we have track, 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 and these wrap cylindrically around the disk, making this weird volume hologram. That's the machine to do that. The important part is we take a single laser, we use some phonic optics to split up multiple incoherent beams because we need some incoherence to make all this work. We split them up, we bring them all together, the disk is living here, and we spin this disk with this thin little optical pattern in space, and then we spin the disk through it, and this is the thing which creates the disk. This is the servo track writer. That's just fun, because it's just complicated optics. We can then put that disk back on the drive, which is basically the world's fastest confocal microscope, because the material's moving through at 20 meters per second. And we can read out the naked disk before we do anything to it. And what we see is indeed we have these planes where we have bright, dark, bright, dark. In each of these little bright tracks is little reflection gratings, and then this thing wraps cylindrically around the disk. So now we've got this disk filled up with tracks. The tracks are still photosensitive, and here's why. Okay, like I said, this is the Jedi Master at that level of manipulating these polymers. We designed the initiator, the dye, to be a big molecule. And we dialed down the amount of it so there was just enough, stoichiometrically, of the initiator to kick off the polymerization process. So when we wrote this original hologram, this is looking in depth, and here's the holographic fringes about 170 nanometers apart. We exactly used up all the initiator in the bright fringes. And of course, in the dark fringes, we didn't use up any at all. This, of course, then caused polymerization to happen and caused some build up some polymer there, and then the monomer diffused back out. And so now we have this polymer grating that's our reflection grating, and that's this big disk full of ones. But where we had dark fringes in the original sensitization, there's still dye lying around. So this material is sensitive, but it's sensitive in a nanostructured way. It's not uniformly sensitive. It's only sensitive in this sinusoidal way. Which means if you bring a focused light in from the top, it will expose, but it can only expose in the formerly dark fringes of the previous hologram. And that causes the same process to get started, but only in the formerly dark fringes of the existing hologram, and you rather a blob now, which exactly fills in the nulls. And this thing goes from reflective to not reflective. And that's just, again, manipulation of the diffusion kinetics and structures of material. So once you get that, and that's just being try that in your materials team for a couple months, then you can fill, this is a case where we just had a uniform grading in the whole space, so just one big grading. And then wherever you write, even though what you made is a blob of polymer, when you look at it in your reflection system, it looks like a dark hole, 1, 2, 3, 4. This is a 6-layer demonstration, just to pretty wide separation in depth, just to show you can do it. It's basic, it's pretty reasonable, it's a 10-micron scale. Once you get that, then you throw that into your machine that makes these tracks. This is a depth scan now, confocal depth scan from this high-speed confocal microscope, which is the drive. So this is depth. These are separated by 90, something like 15 microns. So here was these tracks. Then there's this place where the moire pattern of interferograms canceled out, and there is no track, and there's another track. And then the drive is actually seeing those little tubes of reflectivity and keeping the head focused on them. Then during writing, every once in a while, you turn the bright light on. That causes this further polymerization, which makes this blob of polymer, which no longer reflects. So when you go back and read, you see this little block of reflectivity. So it's getting moderately complex in the structure when you reach down to the material. And it's all done really fast. 50 nanosecond-ish time frames here. The total laser power is around 10 milliwatts on the disk. So it's in comparison to 2-photon, which you could easily do similar things with 2-photon. The difference here is you can have a diode laser, which is economical, and you can go really fast, which is required for the application. No heads exploded, so I'll take this as safe. You can't not talk about holography without talking about display holography, and of course that's, if you've been to an airport, you know about display holography. I thought I'd just show you a little different twist. This actually is using those same materials that I handed out. You increase the monomer concentration a bit so you can get more index refraction change. You can bring the thickness down. If you want to do that for display holography, bragg selectivity is not so good. Oh, there it is. You don't want it to be sub-milliradian selectivity in the readout, you want to be able to show it to your friends, off on the optical label. So you want to make it really thin, order a few microns, which means you need more index refraction to get to high efficiency. But you can do that with these materials by changing the mixer. And this is a company called Zebra Imaging. I can't imagine they're going to be successful commercially, but I think it's really cool technology. What they do is, let's say you're NASA, and you're thinking about some Mars module. And for reasons clear only to NASA, maybe you have to sell this to Congress. You want to make an absolutely gorgeous image of this idea you've got. And by gorgeous, I mean fully 3D, fully color, no glasses required. You can hold it up on the floor of Congress. And literally, of course, taking a photograph of a hologram is kind of nonsensical, but literally pops out of the page, actually. So what you do is you take a computer model of this system, and you figure out on a pixel by pixel basis on the hologram what the local set of gratings would have to be to make that hologram. So you basically do all your holography in the computer, locally calculate what all the gratings would be, and you make yourself a holographic printer that has a couple of extra beams and some facial light modulators, and you print pixel by pixel by pixel the Fourier plane of the hologram that you want. And you can do this really fast because the materials are sensitive. There's no wet processing, so it doesn't curl up and do nasty stuff. So once you've done the whole film, and they can be pretty big because the material is cheap. A little hard to do this with lithium niobate unless you want to invest in some crystal growth. You end up with these just beautiful holograms. Because unlike the good Russians that worked out how to do holography in the 70s with no budget, there's nothing imperfect about these at all, because you do all of it in the computer, and they just print out these little granules. Really, really cool. They're the prettiest things I've ever seen. Again, enabled by some of the capabilities of the material. So that was holography. Step 2 is doing integrated optics, because that's another interesting thing. People did a lot of integrated optics, waveguides and solitons and stuff like that in photorefractive materials. They were sort of science experiments in the sense that because the waveguide didn't hang around, because the photorefractives tended not to be something that was permanent, it wasn't something you would not use too often. These materials, on the other hand, are something you make once and it stays there, so that seems to kind of fit the idea of making devices with them. I'll start simple and work out. This is an Optofluidic device. That's a recent buzzword, unless you haven't heard that before. So the basic idea is microfluidics and optical devices in a single layer. They're usually made in PDMS with standard lithography procedures. We're working on some modifications of that sort of exploit some of these properties. I'm just going to talk, you can carve channels in the material with standard lithography procedures. And you polymerize or wash away stuff that didn't polymerize. But you can leave some sensitivity in the material, the same ways I've talked about before. And so now, as long as you're talking maybe multi-mode optics, so this is 50, 60 micron hole, you can even expose through the cover glass, because you might like to make a slab waveguide out of this using the cover glass as the substrate. And so I get my higher index polymer here, and I can have just literally lay on a chrome mask. I can expose down through it. Where light touches the material, the index refraction goes up. The nice thing about that is it's just beautifully simple processing. In comparison to all the steps that we were showing, this is one step, and you're done. That's kind of nice. And they're fairly pretty. This is an example device, microscope objective. We got a fiber, a multi-mode fiber that's been built into the device over here. That's the scatter in the device. You can turn the lights out if you want to see it better. If you zoom in on it, look in a phase contrast microscope. This is that 50 micron wide channel going all the way across the polymer. Very pretty. Really pretty until you turn the lights on and you find that you have one beautiful piece of dust right in the channel, so you gotta get it a little bit cleaner. But still, this is 12 millimeters long with butt coupling from the microscope and going out to the fiber. Still only about half a dB loss, so they can be very low loss materials, very easy to handle, and that's a nice platform to start with. Okay, now we'll just start playing with lithography techniques, because that's what we do. Let's see, so that was mask-based lithography. What about holographic lithography? So let's take a laser. Let's split it into 4 beams, or into a fiber. Split it into fiber. Do some polarization control, because you got to, because you're a fiber. Have some piezoelectric stretchers here, so we can muck with the phase of a couple of beams. We'll bring all those 4 beams out, and we'll run them together in a pattern of 2 coming in from left and right, and 2 coming in from top and bottom. And as I'll show you next, what that will make is an interference pattern that has essentially infinite depth of field. So we get this interference pattern that's invariant in this direction. Now it turns out that we need that to be really stable, so we'll pick off some of those beams, run over to the camera, interfere the beams so we can see what the relative phase of them are, run it back to the computer, and basically do a slow phase stabilization so that when we make this pattern, it looks like it does in PowerPoint, instead of what it looks like on the rheological table. But really very simple, just 4 beams hanging in space, and there's these columns of light going this way. This is a transverse view then, you just crank MATLAB and say, okay, if I bring 4 beams in, I get them all the same phase, I get this perfectly regular grid of little spots, and that's a nice thing, that go into the page centimeters. And then I hang my material in space. Oh, first I go into camera, I get the whole system running, I put a camera there, and by golly, I can do holography, yep, check. And so that's what the light looks like in the lab. So I then put a slab of this photopolymer in the way. This looks like an egg carton, but again, this is one of these phase contrast microscope pictures. This is a look at the phase of the recorded index structure in the photopolymer. And I get a little blob of high index everywhere I had a blob of light. And what I can go measure that because I gotta understand exactly about 2 times 10 to the minus 3 delta n, so that's good enough to do a reasonable waveguides on the order of fiber optics. A nice dark nozzle, so I got little waveguides here. And what can I do with those? I can make endoscopes, I can make imaging devices, fiber faceplates, if you know those technologies. If you've ever had non-invasive surgery where they cut a little tiny hole, for example, in your knee to go in and muck with your knee rather than cutting a big hole in your knee. And the way they see what they're doing, what the surgeon sees what he's doing, is he has a fiber optic bundle that he images through. Those are pretty expensive, they break a lot, their resolution is limited, all sorts of problems with them. This turns out to be a way to make a single shot polymer replacement that of course is nice and flexible, because that's what the polymers already are. This is a part of an Air Force test chart that we put on the front face of the polymer, and that's what you see coming out the back. And every one of those spots is where those waveguides were. So it's just, and this again is going back to the sensitivity of the polymers, because they're 1 photon processes. This was, I think we had a couple milliwatts of light total on the polymer, and we exposed 1 million waveguides simultaneously in a handful of seconds. This is getting towards the end of the Air Force chart, towards the limit of resolution. So, waveguides, easy. Okay, so we did mask-based lithography, we did interference, or holographic lithography. Let's do direct-write lithography. This is how I made the part that I handed around last time, so this is the same figure I had before. We'll put our part up here, we'll have it on a 3D stage, we'll focus some sensitive light into the material, and then we can just drag that focus around in that 3D and do Etch-a-Sketch for big kids. Now this stuff is going to be important because what I want to do is I want to look into that material and see what's going on in there. So I'll implement a microscope in a color that's not photosensitive because it's not photon energy. And now again, exploiting the weirdness of this material. Remember, it starts out as a liquid and it cures up to a solid. So I can put stuff in that volume before I start. Things like fibers and detectors and lasers and thin film filters and crystals and basically anything I find lying around on my optical table, in smaller, I can embed down in that volume. Why would I want to do that? Well, here's why I want to do that, because the people are funding it. Maybe I made a silicon chip that's supposed to go in your personal computer in about 2.5 to 3 years. And it's going to have optical comm running around that chip so that I can get hundreds of gigabits per second on and off and around the chip. But I do need to get off the chip sometime. And the problem with getting off the chip is these silicon wire waveguides are sub-micron mode diameter, and I don't have any idea where that is when I drop the thing into a package. And I got to get off to a fiber here, and for purposes of illustration, I'm just showing the core of the fiber, which is about 10 microns across. This is about a factor of 100 bigger in area than that, and that would lead to about a factor of 100 squared loss in coupling efficiency, whether it's 0. So I would like to connect from here to here. The modes are the wrong shape, because this is elliptical. They're the wrong size, because this is small, and I have no idea where either of these two things are. So I will embed it in a blob of this polymer, I will reach in with the lithography tool, it's those microscopes that are implemented in red, and I will find this, and I will find that to about 50 to 100 nanometer accuracy. That's not too hard. Once I know those coordinates, then I bring in my cartoon laser here, and I scan between them, and my 3D Etch-a-Sketch means I leave a waveguide behind me. I will change not only position from one end to the other, I also change the power and the shape of that stylus to get a mode that starts out here and changes shape and size when the time it gets over there. And then I carry the whole thing out and I get this little blob of stuff on the material, and now I can talk to this silicon chip with a fiber. Relatively simple application, but hard to imagine to do in standard integrated optics sort of platforms. So this is some examples of us working on that. This is an array of visible light fibers here, so about a 4 micron mode diameter. We've reached in, we've found those fiber cores. Here's the fiber, here's the core. This is, again, one of these scanning microscopes. This is the GIC again, I'm sorry. So we have lots of microscopes. So we're looking down through the solid polymer. We can see the fiber, we can kind of see the core in there. This is polymer everywhere, but this is the index refraction of the waveguide that we wrote once we found the core. Now, when I show this picture, if anyone has ever seen these self-written waveguides and they just jump to the conclusion that's how I did this, we did not put light out of this fiber into the polymer and have it write this waveguide. That would have been cool, except that it wouldn't have worked. One of the reasons it wouldn't have worked is this application is for telecom, for silicon, and so this light has to be 1550. It is possible, but really hard to make these materials respond to 1550. And second of all, we can't do this crazy complexity of steering and changing size and shape with just shoving the light out and telling it to go somewhere. There'd be no control. So instead, we find where these cores are, and then we reach in 3D and write the light. You can see the scatter a little bit off of the waveguide there. So this is the big block of polymer. So we can go look at those things. Let's see what it creates. I mentioned in the pictures I had earlier that the material does absorb, the dot is absorbing. So you better correct for the amount of absorption that you're getting when you reach down deeply in. You can just have your machine change its power. This is a knob in our lithography tool. And you can make waveguides over, this is like 3 or 4 millimeters here, that do not change their mode field diameter, don't change the size of the mode. Or you can adjust this just a little bit and you can start making tapers. And tapers are interesting. Notice the total amount of light here is sub-microwatt. So these are, as I said, pretty sensitive materials. And then you can go look at the modes and decide what they look like. They're literally pretty modes. If you've been trying to build them for a couple of years, they're gorgeous. And you can make a centimeter long part, and it has about 0.7 dB of loss. And because you're an engineer, you like dBs, and so you add things up when you finish. Total propagation loss of around 0.13 dB per centimeter. And that'll finish. Awesome. So that's the wrong conclusion. Must have never edited that conclusion. So I'll just skip the conclusion and say, if you want to make permanent parts, particularly volume parts, where you need 3-dimensional index of refraction control on the high end of a couple hundred microns to the low end of 100 nanometers or so, then these materials are really kind of nifty way to do that. Yeah, I think that was the conclusion. Any questions? Come on.
The polymers are usually used, are they custom built or just buy them off the shelf somewhere? Or?
The polymers, let's see. There's 2 ways you can go. You can buy a fair number of these materials off the shelf. DuPont has been selling a version of these for 20 years. So you look at DuPont holographic photopolymer. DuPont's a little bit hard to work with, so I'll warn you if you go that route. But they are commercially available. They like to talk to people who want to buy $1 billion of material. You may not be able to convince the person that you're going to do that. That is what makes them hard to deal with. But the other thing is they're relatively easy to make. And so there's a fair number of papers out that say this is what you mix together. And if you've got someone who's moderately competent in a camera, they've got the scale and they've got a clean environment and they've got little mixers, it's 2% of that and 5% of this. And so that's the nicer thing, because then you can go in and say, well, I wonder what would happen if I change this a little bit. And it's under your control. So either way, you can buy them, but you can make them as well.
So seeing another thing from the 5P, I think that one thing people try is, if you're writing, the feature sizes you write on your box or whatever, they're a certain size, but if you have a really good, like a stage, you can move the stage around a lot more accurately. So could you draw a really thin feature by drawing something on one side and another thing on the other side, and leaving a really narrow stripe behind, making really small features that way? You see what I'm saying?
I think I see what you're saying. Is this, now are you talking about?
Like say I wanted to draw a really skinny line.
Okay, are you adding two lines and just barely overlapping them?
Not quite overlapping.
Okay. So leave the whole note.
Is that
Maybe. There are versions of these materials, again just playing with kinetics a little bit, that respond with a negative index of refraction, where you have light. So now if you put light here and put light here, leaving a dark spot in the middle, you'd actually have an index of refraction went down, and then up, and then down, and you could maybe, like, for example, guide on that little narrow stripe in the middle. It's my guess that you'd be pressed to get much smaller than the diffraction limit there, unless you start mucking with some of these diffusion reaction kinetics or something, because you do have two diffraction limited blobs of light. As you start bringing those together, you're going to have curves that look exactly like a Rayleigh resolution chart, right? And so as you make the gap between them small, it's going to start to get narrowed down and disappear, unless you start playing with the chemistry to give you something that keeps that from happening, I would guess.
Is it possible to make some material where you can, in one way, make it respond positively, another way, make it respond negatively?
Okay, and you're just setting me up. I know.
Yeah.
Yeah, so that's what I'll talk about after lunch, is how to play a positive and negative process up against one another and get well below 100 nanometer lithography. But Tony knows that, so I got to pay him a buck now.
If there are no more questions, I'd like to make one announcement.